Online participants from many countries, and I hope you can hear me today. There was a problem yesterday, and apparently we have partly optimized the sound. Hopefully today you will be able to listen to me, but if you don't, uh, please turn on your mic and tell us that you cannot hear us. Uh, I would also like to recommend that you kindly, if you have questions, just place it in the chat box. We'll try to respond to it. With this, we'd like to welcome you to the second day. Let's dive into a very exciting field of nuclear magnetic resonance spectroscopy. As we proceed further, it's going to be a bit difficult at times, like a roller coaster. Right? Don't be scared. Life is all roller coasters. This is what we suffer all the day, every day. And we should remind you that we are now right in middle of NMR spectroscopy's first introduction in the context of spectroscopic techniques. Kindly remember that yesterday I told you that like other spectroscopic technique, NMR is also a spectroscopic technique. It's not so uniquely different. It's also interaction of electromagnetic radiation, which is, in this case, radio frequency with matter. In this case, you sample, and radio frequency cause nuclear spin flipping. But the twist was that it took literally decades before NMR was developed, and that was largely because of theoretical and technological impediments. NMR was developed late because there were theoretical and technological shortcomings. Theoretically, we didn't understood why radio frequency going in is not coming out. This was a theoretical impediment. Technological impediment was that radio frequency is really very, very tiny, very low energy radiations. And developing detectors which can detect such a weak signal was a technological impediment. On top of it, NMR is a very insensitive technique, and detecting such a small signal from a very insensitive technique was impediment also. Then development of magnet, which can create the stage for the absorption of radio frequency was impediment. So there were two kinds of impediment. One was theoretical impediment because we didn't really know what and why. We didn't really know what NMR was and why NMR or radio frequency wasn't really absorbed in nuclear spin. And then on top of it, we have technological impediment because we didn't know how to measure such a weak signals. Technological development was not that advanced. And remember, NMR is the physics of weak forces. Everything in NMR is weak. It is the strongest technique. This is the most versatile, most powerful technique. But when it comes to measurement of anything in NMR is weak. Signals are weak. Sensitivity is very, very little. So everything is just so weak. And this is the reason why it's called science of weak forces. And this is the reason why it took so long for development of NMR. And then on top of it, constant technological development, which has really made NMR what it is. I should remind you that every electromagnetic radiation has an energy, a frequency, and a wavelength. And every energy matches some kind of factor you sample. For instance, ultraviolet radiations are good enough to have transition of electrons from low energy to high energy, right? Infrared can only wobble or dance with your bonds, right? Uh, X-rays are strong enough to excite electrons and scatter the light. Radio frequency is just only strong enough to gently flip the nuclear spin. So remember, in order to break a wall, you need a hammer. In order to have a small nail into the wood, you need a small hammer. In order to break the whole building, you need to have bulldozers. Exactly the same analogy. The electromagnetic radiations with different different energies would have a different effect on your sample. And this is the reason why you get different kind of information about your sample, which is invisible, tiny, infinitely small samples, and that eventually lead to collectively information. The NMR spectroscopy is by various factors weak technique. Anyway, so the name is very important, as I mentioned. Nuclear, because it is the nuclear spin. You know, before Zeeman, back in 1800, Peter Zeeman was the first one who said electrons have spins. Everything has a spin. Nuclei also have a spin. The spin means spin, right? Nothing fancy. It's just a very simple word. And he was the first one who theoretically laid the foundation of eventually what NMR became. It was in Max Pauli in 1920s who said that nuclear spins can be up or down. Another scientist contributed. Then was Isaac Rabi who said nuclear spins can be measured. And then was Flex Bloch and Edward Purcell who said, yes, it can be measured and can be recorded. And they developed NMR spectroscopy. So a lot of people have actually worked in this, and everybody got NMRs and the Nobel Prize. So if you work, your chances of Nobel Prize is also very strong. But for that, we need to have a good understanding of NMR spectroscopy. And nuclear spin was a new idea. Placing them in magnetic field was a novel idea because you can only record the absorption of radio frequency when it resonates. And when it's resonating, then radio frequency is absorbed, and radio frequency that can be measured. And therefore, the name is extremely important: nuclear magnetic resonance spectroscopy. Okay, so I showed you that this was a first NMR spectrum, and you can see there are a lot of important elements into it. This is the NMR of ethanol. We know that only chemists know that ethanol, all hydrogens of ethanol are not similar. Only you have the privilege of knowing it. For everybody else, hydrogen is hydrogen, right? Only chemists know that ethanol, the CH3 of ethanol are different from CH2 in between, and OH is in between. because OH has an electro negative atom, and then uh, O is attached to CH2, and then CH3 is without any electronegative atom. So all of them are different because they knew about it through their knowledge of organic chemistry. And for the first time, they have seen these three peaks of ethanol, and they were so absolutely excited about it. Now, I wish to remind you that everything is happening in the stage of NMR where there is a magnetic field, permanent magnet, which was at that time was only 16 megahertz, uh, perhaps 0.8 Tesla or something like that. And then the magnetic field was same for all protons, right? Magnetic field was same for all protons, but three different types of protons, ethanol, are behaving differently. Only chemists can explain that. Nobody else can explain it. So physicists were, of course, disappointed, not very happy with that, but chemists were jumping with happiness. And they were the first one who started using it. After that, biochemists jump in. After that, medical doctors jump in, and now everybody is jumping in. Okay. So the chemists were the first one who start using it. So here you see the NMR spectrum, which is currently, if you have an ethanol sample and if you record ethanol sample, you see something like this. You would see everyone is giving the same response. So you see something like this. You see CH3, CH2, and OH. You get three most important information in it. You get the number of protons, okay, total number of protons. You get which type of proton exists. And I mean, you must be asking me why proton? Why I'm using proton, right? Because hydrogen is proton. Nothing else. The nuclear spin, the nuclei, all nuclei, the nucleus of hydrogen is just one proton. There are three isotopes of hydrogen. One is called protium, the other is called deuterium, the third is called tritium. They're different because they have different neutrons, right? So I'm using the word proton, and all organic chemists, when they use hydrogen NMR spectroscopy, they use the word proton. So I would never use hydrogen again, okay? Forget it. It's just only proton. For me, it's a proton because I'm dealing with, right now, we are dealing with the nucleus. And nucleus has only protons. So proton NMR spectrum, you see the integration? And this CH3 is actually the same because they have the same magnetic and chemical environment. Then the CH2, the integration of 2 is fairly downhill, and then OH, which is only one proton. I leave a question to you. All of these protons are immersed in the same magnetic field. The mission when this was recorded back in 1960s, when there was an electromagnet, before there was a permanent magnet. All of them have exactly the same magnetic field. Why they are behaving differently? Why they appears at different places on the NMR chart spectrum? Okay, one question. You don't need to respond to me, it's not that important. But you see, I want to tell you, NMR spectroscopy has gone through a major development. So right from the first observation of nuclear magnetic resonance in solid and liquid, solid was in Harvard, Purcell, and liquid was in Stanford, both in US, in 1945. And they both of them got Nobel Prize because they published independently in the same journal, in the same issue, and they both got Nobel Prize. In both groups actually got Nobel Prize. Development of chemical shift. They were physicists. They had absolutely no idea what they were doing. It doesn't mean that physicists are very smart people, you know. They knew what they were doing, but they didn't really know how exciting that development was. You know, what they have created has revolutionized chemistry for good, forever. And the chemists then came in and they said, okay, you see, there are three peaks, they are chemical shifts, and they're coupled with each other. Is if there are three different rooms in a house where three identical twins. I've seen Netflix movie of three identical twins who lost somewhere or were given to three foster parents. It doesn't mean that I watch old movies all the time. But three identical twins, CH3, right, in one room. Then there are two identical twins in the other room. And then there is one single OH proton, right? So how many of them, where they live, what relationship they have with each other? NMR is more like a family. Protons of molecules are like families, but they all have their own character. Their character, physicists can never measure. Only chemists can measure their character. It doesn't mean that they have a bad character. They have only different character. Okay. So they were the first one. The chemists were the ones who said, okay, they have different chemical shifts, and they couple with each other. They do have a relationship with each other, and that help you in developing the family structure. That help you to determine the structure of a whole molecule. And then at some point in time, they said, okay, this technique is so absolutely insensitive that they have to do something. So they start working on sensitivity enhancement, they start nuclear over the other specs, signal everything. And in 1970s, superconducting magnets were developed, and FT approach was used in NMR. Computer-controlled instrumentation were developed 1980s, development of multipulse. At this point of time, when someone has really developed FTIR and pulse, Professor Richard Dancy got a Nobel Prize for that too. And it was a quantum jump in sensitivity at this stage when multipulse NMR. And then was gradient use of high sensitive superconducting probes were developed. You would see superconducting probes here in our institute, and major advances in high resolution NMR. Okay, so remember that when the NMR was developed, one NMR was developed in Harvard, which was a solid state NMR. Paraffin. One NMR was developed in Stanford, which was a liquid state NMR, water. So the solid state NMR was developed in parallel to liquid state NMR. But 99% of the applications today are liquid state. You dissolve your sample in deuterated solvents, and then you get spectrum. It's only very recently when solid state NMR spectra start becoming even better. And of course, there were a lot of other developments too. Polarization dynamic nuclear polarization. I'll tell you about it. Increasing the population difference, high resolution MRI were developed for animal research, non-uniform sampling. Now in 1920s, people are now using AI-based NMR. AI pick signals, refine that signal, relate it to some structured feature, help you to develop structure. And God, at this point of time, 1.2 gigahertz, 23.76 Tesla machines are already in marketplace. We have 800 megahertz NMR, which is about 18 Tesla. And now 23 Tesla machines are already available. They're very cheap, about 7 million to 8 million USD. Okay. And of course, now there are improved solid state NMR with fast magic angle spinning available. At the same time, for poor people like us, small benchtop NMR of 60 to 90 megahertz are also available. I've seen one in Foreman Christian College in Lahore. Wonderful 60 megahertz, permanent magnet machine, no superconducting, no helium, no nitrogen, no hustle. Just switch on, put your sample, you get a spectrum. I don't know whether that spectrum would be of any use, but you have satisfaction from inside. That you got something. And then machine learning, they start using machine learning. And machine learning has been used now in modern NMR Advanced 3, in which they now using a machine to decide whether the entire FID has to be recorded, only a certain non-uniform sampling has to be done, and also how many scan has to be done based on the sensitivity. A lot of these new developments underway, AI augmented structural elucidation, you don't need actually, the AI would calculate your NMR, okay, measure, provide you in different solvents, and then you just compare it with the low resolution NMR and you get the simulation of that. So a lot of these development has occurred in NMR spectroscopy, largely driven by sensitivity problem, right? Sensitivity problem. And that is the main driving force in NMR spectroscopy, apart from interpretation, which is the basis of multi-dimensional NMR spectrum. Okay. And these are wonderful, great people. Isaac Rabi in Columbia University, who first measured the neutral spin, he said, can be measured. Then Lockett Purcell, Stanford and Harvard, there were two people who published together, and they were the one who first developed NMR spectrometer, permanent magnet, small one. And Professor Richard Ernst, who was a friend of ours, who came to this institute multiple times, a Nobel laureate. And Richard has actually also written the foreword of our book. If you see the book, the foreword was written by Professor Richard Ernst. And he was from ETH, Switzerland. He was the first one who developed three concepts: FTNMR, pulse, and polarization transfer. He just absolutely revolutionized NMR spectroscopy. One of man he was. And Professor Good Portridge from the same institution in Switzerland. He was the first one. He was actually working from 1970s. He was working on biochemical use of NMR spectroscopy. It was an organic chemistry's ball game. Later, the biochemists thought, why don't we just measure the NMR of proteins and nucleic acids and polysaccharides and just name it. And he was the first one who developed the kind of, not the hardware, the software and per sequences for the interpretation of complex spectrum which come out of protein. You've seen ethanol. How many signals? Because how many protons? Right? Professor Athia's protein has generally 3,000, 4,000, 7,000 protons. And if you see 5,000 protons in the NMR spectrum, you can only go and take a coffee and samosa. Nothing else you can do. You can never interpret. So interpretation was the second most important driving force, and Professor Kurt Bottrage was the teacher of Professor Atia. Professor Atia has actually worked with him in his scripts in USA, and she learned NMR spectroscopy from him, or he learned spectroscopy from her. We don't know. Who cares? But they both have learned, actually. And then there was the medicine. The doctors never want to be behind in whatever you do. Think of it. If you're doing Jadoo Tona, the doctor would come outside with the name of a called Wellness Center. Right? They have a lot of ways of doing it. So doctors didn't really want you to be behind, and they thought, why don't, if they can use NMR for the detection of organic molecules and for proteins and nucleic acid, why can't we use NMR spectroscopy for detections of molecules which are present in body, living organic? Not necessarily human being, can be anything, from primates to rodents. And they got a Nobel Prize in medicine 2003, but the development took place in 1986 when first MRI was developed. Very interesting journey. But see, why bother learning NMR? Why so many of you are just so passionately, with great enthusiasm, coming in train and sitting here, right? Because NMR is literally a response of a lot of your research. If you want to be in the field of research, and especially chemical and biochemical research, there is absolutely no way that you can avoid the use of NMR spectroscopy. It's just so much of applications. So they are the largest users, natural product chemists. You know why? Because they deal with completely unknown molecules. They have absolutely no idea what they are isolating. They dig out something from a complex mixture, and they're the one who are the most curious species of chemistry community. They really want to know the structure of that molecule. No other chemist deals with it. Synthetic chemists, they know if they are putting together these two things, you'll get something, and they have some idea about it. Protein chemists, they already know about it. They already know the sequence of amino acids. They're just trying to get the structure, right? So this is the reason why natural chemists are the most curious part. And they're still the largest users. And then, of course, structural biology, the protein, peptides, nucleic acid, and also dynamic studies. This is a very important aspect of it. Time scale. in any of the spectroscopic technique, the time scale is very important. You know how much time it takes to record UV? Right? 10 per second. You shine UV, everything from the lowest energy state goes to upper energy state. सांस लेने का टाइम भी नहीं मिलता, right? It goes up, it comes down. This is the time scale. You can't do anything except measure the electronic transition from low energy state to a high energy state, from burning to non-burning, from you just name it. It's just spontaneous. Exactly in NMR, IR is absolutely spontaneous. Everything, just you shine, IR, radiation, start bubbling, and energy absorbed, energy emitted. God, finish, halas. Yes, halas.
Yes.
And X-ray, you shine X-ray within 10 seconds, you have a diffraction factor. Is only NMR which is slow, which is so slow that you can have your experiment done in NMR tube and you slowly see substrates or reactants are diminishing, their signals are coming down, and the products appearing. Because it is slow. I'll tell you. NMR time scale is very slow. Very slow, when I say very slow, as compared to UV-IR. So why? Because you excite, right, all the NMR active nuclei, they are excited. Then you give them time to relax back. Okay. It's like, again, they have actually listened to that example 5 million times. Okay. It's like, 3 protons. Here's OH, here's CH2, and CH3. If I excite you, I don't know how to excite you, but one way is to actually make you stand, bring a bulldozer and hit you, right? And you will all fall down. Yes? But you think you would all stand up at the same speed? No? What do you think? You will stand up? It doesn't mean that you will never stand up. I'm sure that you will stand up, but at a different speed. It means that relaxation takes time. Relaxation, when I hit you with bulldozer, and I have no intention of doing it. So there's the energy the kinetic energy has been shifted to you. Right? And then you would wake up, you kind of a relaxation coming back to the thermal equilibrium is going to take time. And this is the reason why NMR is a slow technique. In UV, it's like this. Goes up, goes down. In NMR, it takes sometimes milliseconds, sometimes minutes, sometimes infinite time. There are nuclei would take 500 billion years to relax back. Never relax back. You understand? So this relaxation in NMR spectroscopy is slow. And that is the reason why you can measure the dynamics of your reaction. You can measure reaction kinetics. You can measure equilibrium. You can study biological processes like interaction of small molecule with large molecule in real time. You can measure folding and defolding of biomolecules because it's slow. This relaxation is a slow phenomena, and we will everything which we are discussing, we'll discuss that in greater details. And you get the three-dimensional structure of so many biomolecules. You can use it for drug designing. They've been using it. They'll give you examples of how they use structure-activity relationship, ligand receptor interaction, in vivo MRI is slow. When you place a patient in MRI machine, how long it takes? About an hour, sometimes half an hour, right? Because the process of relaxation takes time, and they keep exciting proton present in water, and then they require spectrum. So it's a slow technique. So you measure electronic environment, building connectivity and orientation through space connectivity by nuclear nerve effect, and so many of that. So NMR is worth studying. And now we come to the fundamental of NMR spectroscopy. You see, NMR is tricky. Not all elements are NMR active. Some of them are NMR active, and some of them are NMR silent. So the NMR active, very simple thing. NMR active nuclei fundamentally are the one which contain either the neutrons or protons as odd number. Either the atomic mass number is odd or atomic number is odd. Either protons are in odd number or neutrons in odd number. Okay. Think of it. Why this happens? Fundamental basic property. When the mass is even and atomic number is even, these are not NMR active. Carbon 12, NMR active or not? Why? Oh, I ask you why. I ask you why. It's not even number. You all are right. Although I haven't really heard of you. But I assume that you're all right. So odd number, odd mass or even mass, even or even, zero, even odd, they are still NMR active. So either the neutrons are NMR active and protons are NMR active. Okay. Protons are odd number and neutrons are odd number. Then only those nuclei are NMR active. Think of it. If carbon 12 is not NMR active, you must be very sad. This is what you study. Organic chemists, biochemists, they have a lot of interest in proton, carbon, to some extent oxygen, to some extent nitrogen. And carbon 12 is not NMR active. Everybody is very sad, you know. But carbon 13 is that one of the isotopes of carbon. There are three isotopes of carbon, right? Carbon 12, carbon 13, carbon 14. Carbon 14 is radioactive. Carbon 13, which is roughly about 1.1% of the total isotopic abundance, is NMR active because it has neutron, which is odd number, right? So it's NMR active. Oxygen 16. Inactive. What about oxygen 15? Active. Or oxygen 17? Nitrogen 14. Oh, God. Active or inactive? Nitrogen 15. Chlorine 19. Protium. Deuterium. Why? Why deuterium is inactive? Active. Now, in this game of active and non-active, tell me which number define elements. Which atomic particle define elements? Proton. Which atomic particle define isotopes? Which atomic particle define ionic character? Electron. So hydrogen has 3 isotopes, carbon has 3 isotopes. Some of the elements, such as tin, has 50 isotopes.
All the 3 types of hydrogen, all of them are active. So why we use the solvent for this organic compound for NMR to be deuterium? And I hope you get my
Yeah. So deuterium, you use it because the deuterium is actually has a different frequency. Okay. In proton NMR spectrum, you detect protium at a particular frequency. Okay. In carbon 13, you also have a deuterium. So you're detecting carbon 13, but carbon 13 signal is split by deuterium because it's an NMR. Now, the question is why they are active. Basic fundamental question. Because they have spins. You know, every atomic particle has a spin. And when they are in even number, they are spin paired. Where they are in odd number, one of them is unpaired. And when they are unpaired, this is called inherent dissymmetry in the overall nuclear spin. So whenever there is an unpaired nuclear particle, nucleon is called nucleon. Any particle which exists in nucleus is called nucleon. And when there is any of the subatomic particle is unpaired, then there is an inherent dissymmetry. As a result of it, the nucleus starts spinning around the axis, its own axis. Okay. That is the fundamental property on which NMR spectroscopy is based. Of a nuclear, if any nucleus is not spinning, it can never be detected by NMR spectroscopy. And unpaired nucleon are fundamental requirement for a spin. Okay, for a spin. Now the question is that if you have a nuclear spin, okay, They are spinning like this on their axis. On their axis. Remember, the Earth has two different movement. One is axial movement, which make day and night, and the other is orbital movement, which define weathers, right? Exactly now, every odd number, odd mass, or odd number molecule theoretically would have an axial spin, right? And this spin is called magnetic moment. Magnetic moment, because these are now behaving like a small tiny magnet. And when they're behaving like a small tiny magnet, this is what you need for NMR spectroscopy. Everything will depend on nuclear spin. Okay. And the property which eventually comes out of it is called the spin quantum number, which we will discuss. Now, you see, take some most common elements. Proton, right? Spin half nuclear. NMR active. Deuterium 1, NMR active. Carbon 12, NMR inactive. C13, NMR active. N14, O16, O17, and F19. E31, they are the common nuclei which we study. And when they have nuclear spin, you use this formula, it's called the spin quantum number. And this spin quantum number, if you fit this spin quantum number in this formula, 2i plus 1, you would know there's going to be two different spin states. And hydrogen would have three different spin states. Of carbon 12 would none, C13 would have two, N14 would have three, oxygen 0, oxygen 17 will be 0, and F19 is 2. But where it will happen, the question is, why it was not detected? From the beginning of the universe till 1945, they were like this, okay? But they were like this. They were spinning along their axis, but in all directions, okay? They were spinning in all directions. This was a crowd of nuclei with every direction, with no orientation, called degenerated state. Completely in equilibrium of zero magnitude. When they were placed accidentally under the magnetic field B0, permanent magnet, electromagnet, and superconducting magnet, these nuclei quickly aligned themselves, some of them along the magnetic field, aligned to the magnetic field, and some opposed to the magnetic field. The one which aligned to the magnetic field, a low energy state, which is called alpha energy state. The one which were opposed to the magnetic field, they were in high energy state. This is exactly when you bring compass, it would certainly orient around the north direction, right? The same thing happened because they are magnets. And these magnets have to survive. And when they are placed under the magnetic field, they divide themselves into two quantized states, at least two quantized states. There are elements which divide themselves into 7, 8, 9, 10 quantized states. We'll discuss this later. But dipolar nuclei would divide themselves, millions of them, trillions of them. Some of them will align with the magnetic field, and some of them. And now the alpha state and beta state. In NMR spectroscopy, the low energy state is shown up and high energy state is shown down, very different from UVIR. Because the magnet is vertical. You would visit the NMR laboratory and you would find that the machines, the magnets are like this, right? So the magnetic field direction is vertical. So the B naught is always up. And when B naught is up, anything which is aligning to the magnetic field is low energy state, alpha state. Anything which is opposed to the magnetic field is beta state. I wish to remind you that this is the simplest case. There are many, many elements which divide themselves into 7, 8, 9, 10 different stages. And they're like this, right? The most closest, least closest, most opposing, least opposing. This is called quantized energy states.
Why do we have two type of this orientation? Okay, we have the vertical magnetic state. Right, you said some of this nucleus with the same direction. Okay, the other in the opposite direction. Why did you take this up?
Yeah, that's a very, very interesting question. You see, all of them, they are in Earth's magnetic field.
The same.
Yeah, it's like UV, huh? No. Okay. The degenerated states, when these elements, they are in Earth's magnetic field. These nuclei have different orientation. The one which are closest to magnetic field will align themselves to that direction. The one which are opposed to the magnetic field will align themselves to the opposite direction. You see, there are just a crowd of nuclear spin in every direction. They have different energy. They all have different energy. The problem is that you cannot measure it because there are millions of different energies. When you place them in the magnetic field, they align themselves to two directions. The group of magnets, group of these tiny little magnets, which are closest to the direction of the applied magnetic field, will align themselves to B naught, and the one which are opposed to the magnetic field in terms of energy will oppose to the direction. So they all have different kind of orientations. But when the magnetic field is applied, they divide into two. And it's not necessary there are two. There are many magnets, it's called quadruple nuclear, which has more than two nuclear states. They have 7, 8, 9, 10 states. There is no clear division that only one alpha state and beta state. They can divide themselves into 7 different stages of each quantized energy. They're called quadruple nuclei. We'll study that. Now, this is exactly what happened in 1940s when the NMR spectroscopy was developed. This is the magic. What it means, when there are certain nuclei which are aligned to the magnetic field, they are in alpha state. Whereas certain nuclei which are opposed to the magnetic field, beta. Now one is low energy, the other is high energy. Stage is set. This is exactly what you want for radio frequency to absorb. No electromagnetic radiation can absorb without energy difference. If there is no energy difference, no absorption of radio frequency or any radiation per se. UV, IR, nothing would be absorbed unless there are energy states. So the first thing happened when you place your sample in permanent, ever-present magnetic field is defining of energy states. And when energy states are defined, you can bring radio frequency, you can absorb radio frequency. Some of the species will go from low energy state to high energy state, absorption of radio frequency. And that was recorded. That was the first NMR was an absorption of radio frequency because of the presence of magnetic field. The two energy states were defined. Okay?
I think there is maybe there is some regulation between nucleus between each together. For example, these nucleus and nucleus, we have magnetic field. There is okay. You might take the same direction. I might take the other the opposite direction. Maybe there is regulation between us.
Negotiation between
Yeah.
it has not been discovered yet, but envision that you have needles spread all over, okay? And these needles have different kind of charges. You bring a magnet, some of them will be the positive, north will be with the south will be with the north. Simple analogy. The analogy is that when you have degenerated states, the simplest form is that the ones which are closest to the energy of that direction will go to that direction. And the ones which are closest to the other energy level will go to the opposite direction. But this is not the case only, For instance, deuterium has 3 different stages. Okay? And similarly, the other elements have like 6, 7, 8, 9, 10 different stages. So they are quantized energy states. And these nuclei, which have spin half nuclei, which are only up, alpha, and down, beta, low energy state and high energy state, they call it dipolar nuclei. So hydrogen is a dipolar nuclei, carbon 13 is a dipolar nuclei, and 15 is a dipolar nuclei, P31 is a dipolar nuclei, F19 is a dipolar nuclei. But there are many, many nuclei which are more than that. Deuterium has 3 different stages. Okay, boron has 4 different quantized states. So the nuclei, depending on the elements they have, would have a different type of orientation. So, nuclei with odd mass and odd or even number possess the spin quantum, as a fractional integer, such as nuclei with spin quantum number high with 2 allowed spin states. They call dipolar nuclei. Nuclei with odd mass and odd number, such as O17, are NMR active with nuclear quadruple. Their natural abundance is very, very low, right? You cannot really measure it. Even for C13, C13 was, NMR was developed for protons. And it was only in 60s and 70s when NMR was developed enough that people start detecting C13. They were very, very interested about C13. But C13 is only 1.1%. So photon is about 99% is proton. Carbon 13 is only 1% carbon 13. Proton is 4 times more active in terms of baromagnetic ratio, 4 times more sensitive, and 99% abundant. that proton is the easiest to detect. Carbon-13 is 1/4 of a gyromagnetic ratio. It's a very weak nuclei and is only 1%. But imagine how eager chemists were to detect C13 and how much time they have actually taken to develop the C13 NMR spectroscopy. You know, FT NMR was developed, pulse NMR spectroscopy, signal averaging. Okay, so N14, what do you think about N14? Even mass and odd number, spin quantum number. And it has like 3 different stages. Is NMR active but hardly detected? I'll tell you why. NMR is extremely different from the other spectroscopy technique. In other spectroscopy technique, everything is in low energy. It absorbs and it goes to the high energy. All species are in low energy. And the energy difference is just phenomenal. UV is roughly about 70 to 140 kilocalories, kcal, right? So much of energy. Infrared is about 4 to 5 kcal. NMR is 0.04 calories. It's extremely weak, you know. The difference between low energy to high energy, if you bring UV, you give this energy, everything goes out. It's a huge difference. All population from low energy state to go to high energy state. The signal is just like this. Because there is population exists only on low energy state or high energy state. NMR is absolutely different. In NMR, you have seen by yourself, both population states are populated. Both energy states have population. Right? The low energy state has neutral spin, high energy state has neutral spin. The difference between the population is so little that it's so difficult to measure that. And that is the reason why I said this is the science of weak forces. You need to have super sensitive detector in order to measure absorption in fraction of a calories. Fraction of calories, right? Less than 1 joule. It's just a very, very small energy which you need to discover. Where you have two energy states, dipolar nuclei, you have population here and here. The difference between population is something which you can measure. If you have 3 states, 4 states, the population is divided into 4, 5, 6, 7. And when population is divided in 4, 5, 6, 7, the energy difference between them is just even smaller. And the sample is detecting the difference is even difficult. That is the reason, despite the fact that all nuclei with odd mass and even number, odd number and odd mass, so-called nuclear particles, they are difficult to measure, right? And I give an example. If you have 2 houses and the number of children in 2 houses, okay, it's little different. One has 7, the other has 6, right? If you bring one child from one to the other, you need energy, right? Children are very naughty. We need to push them up. And if you have 3-4 houses without any wall in between. Nobody knows whose children is who. So you would know it, you would have no idea which nuclear spin is going where. The difference between the nuclear spin in quantized state, which are quadruple. Quadruple nuclei are the one which has more than one energy state. Okay. And they are very difficult to measure. People are still measuring them, but it requires super fast machines. And then nuclei with mass, even number, they are zero spin and not NMR. Now, what happened actually? Which nuclei have the property of a nuclear spin? Question for you. Which nuclei? Okay. Odd number of protons, and odd number of electrons. What happens is that when you place magnetic field P naught, yes please.
सर हम NMR एक्टिव और नॉन एक्टिव स्पीशीज में तो डिफरेंस कर सकते हैं तो आपने एक NMR साइलेंस स्पीशीज का भी जिक्र किया वो क्या?
Hey, NMR inactive are called NMR silent. Okay. Remember that in periodic table you can detect every element. You just need to choose the right isotope. Okay. If carbon 12 is not active, carbon 15 is inactive. If if oxygen is not active, oxygen 15 is active. Okay. Similarly, every element has at least one isotope, which is NMR active. Okay. And that is the reason that NMR is so powerful that now there are probes available which can detect number of other nuclei. They are general probes. Probes are a small cylinder which detect the signals coming out of the nuclear species which you are trying to detect.
So is it possible to change the direction of magnetic field?
If you change the direction of the magnetic field, you will change everything else. It has been done. For instance, in case of MRI, the magnetic field is horizontal, right? So in solid state NMR, the sample is tilted. It's called magic angle split. But it's more convenient to have a magnet which is horizontal.
So why would they always? So why don't they always take upward direction? Magnetic field.
Excuse me?
सर हम हमेशा मैग्नेटिक फील्ड को ऊपर की डायरेक्शन में अगर ये नीचे की डायरेक्शन में होंगे तो जिस तरह हमारे बाकी स्पिन स्टेट होते हैं वो वैसे नहीं निकल पाएंगे बीटा को मूव कर सकते हैं
No, but you see, the magnets are built in a way, आप उन्हें उलट भी सकते होंगे. But you see, you don't need to worry about the alpha state up or down state down. This is just a representation. It doesn't mean anything. It's a representation. The nuclear spin which are aligned with magnetic field are low energy state, right? And nuclear spin which are opposed to the magnetic field are higher in energy. So it's just a representation. You don't need to worry that we have actually changed the direction of anything else. We have actually changed the direction. We just representation of low energy being shown up and high energy being shown down. Right? And I'll tell you why, because later we would also be discussing the nuclear spin in terms of pulses, of a block and television vector. Okay, so what happened is that before the magnetic field, all nuclei were spinning around their own axis. Right? When you place in the magnetic field, two things happen. One is that they start dividing into energy states, and second is that they start precision around the magnetic field. This is called orbital or angular spinning. परेशान हो गए?
की वजह से नजर नहीं आ रहा।
Oh, I'm sorry. आपने बड़े देर से बताया। आप नजर आ रहे हैं? It's okay? Okay, so this was the angular movement was discovered for the first time by a scientist called Joseph Larmor. And in recognition of his contribution, this is called Larmor movement or a Larmor precision frequency. So what happened is that before the presence of, in the absence of magnetic field, the nuclear spin of NMR active nuclei were spinning around their own axis in every direction. When you place the sample in magnetic field, they divide themselves, simplest form, dipole, two different energy states. And at the same time, they start precision like this. Okay? And they use the word called toppling gyroscope. Right? Toppling gyroscope when it's about to fall. So this is for Larmor frequency or omega, which is directly proportional to B naught. B naught is the magnetic field. The more strong the magnet is, more precision would be. Right? The stronger the magnet, faster the angular moment, precision frequency. Right? So this is directly proportional. This is directly proportional. This angular momentum or this precision frequency is directly proportional to B naught. And proportionality constant is replaced with delta, magnetic gyric ratio. Magnetic gyric ratio is a very important concept in NMR spectroscopy. Is a very straightforward equation. You have a strong magnet, more precision. But it doesn't mean that all the elements would have the same precision frequency. When you have a permanent magnet, and if you try to have different kinds of metal, steel, iron, gold, copper, you think the magnet attract them with the same speed? Or wood? No. You know, the response to magnet is different by different elements. The magnet is the same, but response of different elements to magnetic field is different. Exactly if you have a permanent magnet and you bring pairs of different metals, they would have a different response to it, right? Exactly the same account, the different elements would have a different response against magnetic field. And this is called gyromagnetic ratio. It was experimentally measured. Experimentally measured, but it's not a magic number. It can be calculated for elements. It's called mass over charge ratios. So the more magnetic field, stronger the magnetic field, the stronger the precision frequency. Let me remind you again. When there is no magnetic field, NMR active nuclei are in all orientation. They are degenerate. They have no defined orientation. Therefore, they cannot absorb any radio frequency. When you place them in the magnetic field, When you place them in magnetic field, they divide themselves into two or more quantized energy states. Okay? When they divide into quantized energy states, they can absorb radio frequency now because you can move from one to the other. Second is that now at this stage, they start precision. Precision. Every element would have a different precision because they have a different magnetic equation. Their response towards magnet is different, right? Now, but in hydrogen, in ethanol, why the precision frequency is not same for all? For all photons, the precision frequency is the frequency which need to match with the radio frequency. When you give a radio frequency, only that radio frequency which matches with precision frequency will be absorbed and it goes into the high energy state. Okay? This is a very simple quantum physics. Quantum physics says that if you wish to transfer energy from one type of radiation to the other species, they have to move in the same direction. And Dr. gave a very interesting example. This is your radio frequency. It has energy, right? Particle. And that photon can only be transferred from radio frequency to lower frequency which matches. So for instance, if you have this small sandwich in your hand, which is an energy, and you want to transfer that into the other hand, which is also moving in the same direction, it has to be matched. When it matches, then you will be able to transfer that. Okay. If it doesn't match, it would never be. Okay. So only when precision frequency, this frequency, matches with the radio frequency, then only absorption will take place. Okay. Radio frequency will only absorb when it matches with the precision frequency. Now my question to you, how come on the face of the earth the precision frequency of 6 protons in ethanol is different? This is half of the NMR. If we understand this concept, we understand half of NMR. That photons are not same. Photons have different electronic environment. They have a shielding of electrons around them. Some more, some less. The one with the electromagnetic atom would have less electrons around them. And the one without any electromagnetic atom would have more electrons around them. As a result of it, they are different. But most importantly, the B naught is not same for them. B naught is same for them, but they don't feel it. They feel differently. The one which are very shielded will feel less B naught because electrons have a counter magnetism. The one without much of electrons, such as hydroxy proton, would feel more B naught, right? Because it has less shielding around. And that is called B affected. B naught is same for every, B naught is ever present, same is called magnetic flux density. Magnetic flux density is never changed. In all NMR spectrometer, when it is they are commissioned, their magnetic field is fixed forever. These machines are, since the commissioning to death, they have the same magnetic field density. B naught would always be safe. If there is a drifting, there is something else wrong with the machine. The B naught is safe for everything. But B effective is different for CH3, CH2, and so on. When B effective is different, here instead of B naught, you say B effective. And when B effective is directly proportional to precision frequency, they will have a different precision frequency, isn't it? The precision frequency would be different because they're feeling different magnetic field. And where they're feeling different magnetic field, the precision frequency would be different, the radio frequency would be differently absorbed, and they would have not one signal, but three signals. This is exactly what chemists were able to define to physicists. Let me repeat it again because this is a fundamental concept. In order to bring this, these nuclei, which are aligned to the magnetic field, alpha state, to the beta state, they need to absorb radio frequency, energy. This radio frequency has to match with the Larmor frequency or precision frequency. Precision frequency is directly proportional to magnetic field. Magnetic field is same for all elements, but they feel differently. This is called B effective, right? And that is the reason if you have 3,000 protons in your sample, you could have theoretically 3,000 peaks, unless they are magnetically equivalent. Because they would have 3,000 different type of precision. Okay, if you have carbon 13, 30 carbon 13, the 30 carbon would have a different electronic environment, and they would have different B effective on that. As a result, the precision frequency would be different, and they would absorb radio frequency differently. As a result, you will see a different signal. This is the key of NMR spectroscopy. We will be repeating that again, so you don't need to worry about it. The only thing which you need to remember is that number one, all protons, all elements have at least one isotope which is NMR active, because it has either odd mass or odd number. Second, within the same element in a molecule, they have different microelectronic environment. And because of microelectronic environment, they have different B naught, B effective. As a result, they would have a different precision frequency and they would appear different. If there was only one signal, it was completely of no use for chemists. Since there was three signals for ethanol, they were able to use it because they know exactly that, and that is the basis of the structural equation. Because when you see different signals for different protons, only then you can construct a molecule. Okay? So this is the baseline, but we will repeat it again. We'll see it again. Okay? Any question? Yes.
Before any nucleus have two type of movement. The person of the spirit and its second one its orbital. So how we can how this orbitals, how we can control or remove like this?
Why would we like to remove? We don't remove it.
How it be response to the magnetic field? Yes, influence or
Okay, in the absence of magnetic field, there is no precision. In the absence of magnetic field, there is only axis, around their own axis, every direction. When you place these nuclei or your sample, in magnetic field, the nucleus spin along with the axis they also start precision. You know why? Basic fundamental fact. If a small tiny magnet has to survive in a large magnetic field, it has to do something. Right? Survival required this precision frequency. Okay. So this precision frequency, which is also called Raman frequency, is the key to NMR spectroscopy. But this because this is measured, nothing else is measured. Only this is measured. This Raman frequency, and how you measure it? By radio frequency. Right? Radio frequency is only the tool of measuring the Raman frequency. Radio frequency has nothing role, no other role but to measure the Raman frequency. Okay?
For the rotation, what is
Okay, so colleagues online, do you have any question which you would like me to respond to you? Here, chat box, please. Yes, please.
Do we have elementary particles of magnetic field? जो मैग्नेट का मैग्नेटिक फील्ड होता है क्या उसके कोई एलिमेंट्री पार्टिकल होते हैं या ये जस्ट virtually
You see, magnetic field is a vector, and magnetic field is actually generated by, as is a superconducting magnet. This is a alloy of a niobium with tin. And when you give electric energy at a liquid helium temperature, we will study that, it becomes a magnet. So like permanent magnet or electromagnet, superconducting is a magnet also. And remember, magnets are always vectors. Magnets, magnetic properties are always vectorial properties. This is the reason that you call it like this. Okay. Similarly, the nuclei are also small magnet, right? So it is an interplay of a small magnet in big magnet. When you place a small magnet in big magnet, what happened? This is what happened. When you place these small, tiny little magnets under the strong magnetic field, they start precision and they start aligning themselves to different stages. In dipolar nuclei, only up and down. In quadruple nuclei, they can be of different quantized. You're asking about if you're asking about the fundamental particles, I don't know whether you've studied atom. I know that electron is a fundamental particle. It cannot be split. But proton is not particle. It is a complex particle. It has quarks in it. Neutrons have a quarks in it also. Neutrons is electrically neutral, but it behaves like a charged particle when it is under the magnetic field. Right? This is the reason why odd number of isotopes, odd number of neutrons are also split.
Sir, a couple of questions here.
There is one question, yes.
The P naught and the P
Effective.
are they the same?
No, they're not same.
How do you measure?
I forgot to give the example which I always give since last 100 years. Okay, again I take these three shapes. Two from Egypt, one from here. Okay. They are on the south pole or north pole, whatever you like. Minus 50 degrees centigrades. Right? This is B naught. For them, everything is same. The temperature is not different from them, right? But one is wearing a fur coat, a big thick fur coat. The other wearing a wool coat. The other one is wearing like a t-shirt. Okay. Hydroxy is a t-shirt. CH2 is a woolen coat. And CH3 is a fur coat. will they experience or immerse in will they feel the same V naught temperature? Exactly this is. For them, temperature is same, but they're feeling this temperature differently depending on the electronic code they have. The more thick electronic code is, less V naught they feel. Because electron has a magnetic field which opposes the magnetic field of V naught. Right? So the more electrons, less V naught, less field.
How is the PF made? Is it the same as the Lama frequency?
Excuse me?
The B effect. The B effect.
No, be effective. Remember, the Raman frequency is directly proportional to magnetic field. Okay? More the magnetic field, more Raman frequency. So if B effective is different, the Raman frequency for all three of them is different also. Okay? Yeah, it's directly proportional. And therefore, Raman frequency is different. They would resonate differently because they would absorb radio frequency differently. Okay? Yes.
So if the car has person.
Okay, so the question from Dr. Star is the nuclei of a same element. It means same element, like hydrogen or carbon or nitrogen, are same in nature. Then why do they orient themselves into two different states with different energies? I told you that although they are different, although they are in different, in the absence of a magnetic field, they have a different orientation. You know, they are in all different orientation, but they have different energies as well. You know? There is an ever-present magnetic field which is called Earth field. Remember, Earth has a magnetic field also. There is Earth field NMR available now. You don't need any magnet, right? So Earth field, some of them, they have different energies. And when magnetic field is placed, they align themselves along based on their own inherent energy which they have. Some of them are closer to the aligned magnetic field, and some of them are opposed to the magnetic field, depending on their energy. And if you want to move from them from here to here, like a compass needle, if you would like to move compass needle from here to there, you need energy. And that energy is radio frequency. Okay? So, yeah. Let me first respond. Each CH4, each same different, same chemical environment CH4, because they will all be oriented they will all be oriented in two states, right? So you have, they have a methyl would have a signal also. Methyl would have a, but it will not be splitted because all protons are the same electronic entity. Any other question? Yes.
About you have is it about the shell, the shell. The electrons can affect about the proton and can be shaped the environment.
Chile.
Yeah. If we have, I am talking about if there we have concentrated solution with the same compound. Can any compound like this kind of magnetic field? We have this compound and the same compound. This compound can change the compound. And about when we put the patient inside this MRI in the hospital, they can take the magnetic field can affect also inside the or only on the surface.
So let me respond with a very interesting question. You see, in MRI, magnetic resonance imaging is exactly the same theory as NMR spectroscopy. In 70% of our body is water, and water is measured. Water has oxygen and hydrogen. Hydrogen is proton. MRI is a proton NMR spectrum. Okay? Proton NMR spectrum. Proton of water is measured. Under the magnetic field, the proton nuclei orient themselves in the magnetic field. Radio frequency is given. When radio frequency is given, relaxation takes place. The spectra is recorded. Spectrums are recorded, accumulated. Every tick is one spectrum, and you accumulate thousands of these spectrum together. It's called signal average. When you record that, you record proton NMR spectrum of the orbit. Philosophy is very simple. Proton water is the concentration of water is more in abnormal growth. When there is a cancer, the metabolic activity of cancer cell is higher than the normal cells. And there's going to be more water in that. So you get the image of a proton where you can see the concentration of water more than the normal tissue. And that is the cancer. Abnormal growth, right? So it's a proton NMR spectrum. In abnormal tissues, abnormal growth, uncontrolled growth, the metabolic activity is much higher than the normal cells. More water in, more sample. You see a condensed red spot in contrast MRI of abnormally large number of protons present in water, that particular. Okay. What was your another place?
We have this compound and this compound, and we have magnetic field. And this compound also shields.
Two compounds.
I guess have the solution to can not only the electron can shade the protons, also another form around the target compound, and also shield the magnetic field.
Well, I would like to have two compounds together.
When you measure it for any mark.
Well, it can be an experiment, you know. In my own understanding, anything which is out of the box, like his thing, is the beginning of an exciting science. So he's proposing that if you have, I mean, these people are just measuring one compound. If they have two compounds, like two different, if they have two tubes, one tube inside the other tube, what will happen at the end? No, but this makes sense.
Yeah.
This makes sense. It makes sense also that the other compound would have some influence. Even if you can have two compounds in one mixture, there's going to be some kind of an interaction. Intermolecular interaction is so important. Even solvent is another compound, right? Solvent in which you dissolve your compound is another compound. Solvent would have effect on your, if you have paramagnetic, we would study that also. You see, in certain cases, relaxation is so difficult that they have to add some kind of paramagnetic compound in order to facilitate. So these compounds would have influence on the other. If you record NMR spectrum of steroid, cholesterol in water, it looks different. If you record in DMSO, it will be different. So there is an influence. So I agree with you. Thank you, sir.
We were kind of for the MS study. Now capillary.
Yeah, so about 60 years ago, when Dr. Atia was learning NMR, people used to use trimethylsilate because there was a need of a reference which was zero, and then everything was measured with reference to TMS. So they used to add TMS into the sample. What a terrible thing it was, you know, having your pure compound and adding impurity into it. And then after that, when they start doing it, they start putting a small capillary of TMS inside to get the same result. But in this case, you can just take out the capillary and you know. So she's right. Anyway, yes, sir.
ये मैंने मैंने मूव कर रहा था किसी भी डायरेक्शन में
Yeah, ये लापर frequency नहीं move कर रहा था.
नहीं सर मैं काम कर रहा हूँ
Hey, listen. Laper frequency doesn't exist in the absence of. It's just axle. You know, axle means that you have a ball which is just moving in its own axis. But when you place that tiny little magnetic ball in, it is a vector, right? Magnet is a vector. It has a direction. So even axis movement has a direction. When you place that magnet into a larger magnet, V naught, then start processing around the direction or opposed to the direction. It's called precision. Okay?
That's like top.
Huh? Yeah, you know, I mean, my father never let me play Lattu, so I don't really know much about it. I'm sure that her father was much more liberal. I don't know why Lattu is falling. You know Lattu? Guys,
They know Beyblade.
yes, you know, so this. Nobody can explain it. I hear this. I will the last person. My father never let me play. You know how to do that. Yes, please.
I have patience. I have patience.
He has a question.
I have a
Yeah, sure.
My question is this. First, you maybe I stand up so that my voice. First, from your lectures, we use E effect, we record E
B
effect
effect.
as the signal. Am I correct?
No. You see, please have a seat. The frequency, the louder frequency or precision frequency is directly proportional to this frequency. Is directly proportional to B naught. Okay. The stronger the B naught, more faster would be louder frequency. Right? But B naught is not same for every photon of a sample. Why is not same? Because they have different electronic environment. So a new term was invented, which is called B effective. Effectively, they are experiencing different magnetic field depending on their own electronic environment. And B effective is then directly proportional to louder frequency. So louder frequency is measured. In NMR spectroscopy, the louder frequency is measured.
That's nice. And the next question is this measure for each chemical environment differently or all as the value?
That's a very good question. Okay, so in ethanol, classical NMR spectroscopy was that in ethanol, you have three different louder frequencies. So radio frequency, like a radio, exactly like a radio, And I can show you that also. I have a slide. But far away, a lot more. Yeah, hang on. Okay, sorry, I can show you that. This is the axle movement. Sorry, I had that. I've been struggling. And then this is precision frequency. Precision means a regular angular movement, and it's named as lava frequency. Just in recognition of the just to do first gratitude. Okay. And this lava frequency is directly proportional to the magnetic field they experience, be affected, right? This is what you measure. Now in ethanol, you need to have a radio frequency which match with three different lava frequencies of three different types of. So the machine which was used earlier was this one. We have in our institute also this one. Okay. This is permanent magnet. See, sorry, this is electromagnet. Permanent magnet, different. This is electromagnet. Your sample is inside here. Okay. And again, everything is same, lambda frequency. This is radio frequency oscillator. You slowly increase radio frequency. When it matches with CH3, absorption we call it. Here. This is a paper chart. First absorption required. Then when is increased, it matches with CH2, second peak required. When it matches with OH, second, and if you have a sample with 30 different protons, you become fossil here. Standing and feeling almost fossilized. You have no family, no children, nothing. But this is the work. And that is the reason why they have changed the whole philosophy of NMR. That was a good question. Yeah. Anything else? Yes, sir. Why we are not getting questions from parents? Why only sir? Yeah. I think they understand everything. Yes, sir.
Here you are tiny magnet inside a big magnet, and the V naught is always constant. The applied magnetic field is always constant. That is not it. So why our UPI are undergoing criticism? Why are they getting? Why causes their rotation? They could be aligning somewhere opposite upward or downward. Why are they
Okay, so the question is why precision frequency? Why they just remain static, aligned, or opposed? Why they have this weird Sharati movement? Like this. Okay, so this is the behavior of a tiny little magnet which is trying to survive in a large. It's a natural behavior, right? Exactly on the planetary movement. Think of solar system. The sun is a big magnet, B naught. Okay. So why Earth is not static? If Earth remains static, it will just go and get into sun, will become integral part of sun. In order to survive, it moves in planetary orbital mode. So when tiny little magnet like Sun, Earth is trying to survive against a big magnet like a solar system, that is called orbital mode. Right? So this is exactly what happened. The precision frequency is the survival technique of a small little magnet under the influence of a big magnet. And remember, I want to tell you, you see, if you in MRI, the maximum magnetic field which is available is about 4 Tesla. The machine which are available in chemistry is about 23 Tesla. So if you place a person inside real NMR, somehow, person, then it will really blow out everything. So what I'm trying to say is that precision frequency is a natural reaction of a tiny little magnet under the influence of a big magnet. Any other question?
CA3 के लिए alpha और beta spin state अलग होगी difference between alpha and beta spin and CA2 के लिए separate कम होगी थोड़ा idea हमारे पास हो.
Absolutely not. So is again a very important question. I must appreciate that you're really asking penetrating question. The question is that for ethanol, which has 3 different types of protons, the population difference between alpha and beta state will be different. No, absolutely not. The only thing which will be different is because what? Why? Only chemists know about it.
We need to have this slide. We have to slide.
Yeah, please. Okay, so Dr. Atif Zahoor has in his lab 20 megahertz permanent magnet NMR. You know, 20 megahertz is a small benchtop NMR, which is like this big. Okay, and to determine solid fat index, we put sample in tube at 20 degrees centigrade. We tell us the results in percentage. What actually we are measuring photons of fat in liquid phase in absolutely 20 megahertz. We can't measure anything else except photon. Is 20 megahertz is such a low resolution that it can only measure the most abundant element, which is hydrogen. Hydrogen is 99% hydrogen. Sorry, hydrogen is 99% proton, which is that. Yes, you are actually recording the proton NMR. Dr. Azaz Ahmed, OH can be seen if you work with NMR solvent that does not have extinguishable proton. For example, you deuterated methanol to analyze ethanol, then you won't see OH. Yes, absolutely. He's absolutely right that ethanol was a neat ethanol. If you the spectrum which you see is called neat. Neat means that there was no solvent added. But if you add a deuterated solvent, OH will be changed, exchange will be changed. You know, all isotopes are same chemically, but magnetically they are different because their nuclei are different. So a deuterium would not be that. When you're trying to read proton, you can't read deuterium. When you're trying to read carbon, you cannot read proton. When you're trying to read nitrogen, you cannot read any other element because the Raman frequency is fixed. They are very different, and therefore So when there is OH replaced with OD, you will not be able to see OH. Okay? Any other?
Active again.
Sir, proton NMR of fat in liquid or in solid phase at a given temperature, depending on if you dissolve, I assume that you don't have a solid state probe, Dr. Akib. I think you're probably dissolving fat into some other solvent, and you are recording the proton NMR of liquid phase fat soluble, soluble fat.
Yeah.
Solid state NMR are really very specialized and they cost a lot. We don't have it yet. We have been trying to have it, but we don't have it. Any other questions from the girl side? Amna.
You know, one minute about this class, about our patients. Thank you so much for this lesson class. Yesterday you brought out an important thing for the PhD student patient, but we have it to the lab. That we are, I am here, this is the second step here. We have completed many times about this thing.
You get that.
No, I missed what we, if you see here in this, only infant students get practical course or to deal with all the techniques. But the PhD student, especially who is coming from outside, in another city in Pakistan, or like us, in another country, no classes like this, right? Or not allow us to get any training about using this technique. And about also in class, I don't know, it is just visiting that the NMR or us to that experiment like this.
Let me ask for that. Yeah, students are students, right? So I think they should all get the exposure, right?
Then in NMR lab for all the students, all.
No, he probably talking about short-term results. That is not happening. So I think we should develop some system. Thank you, sir. That's it.
Thank you.
Yes. Yeah. How can you measure it? You measure it by the chemical shift. No, be effective is practically what proton feel. And if they are shielded, they feel less B naught. So their B effective is less than OH. Okay, so this is how you measure it because the chemical shape is going to be different. This is exactly what you measure in NMR. Thank you. Thank you very much. Mr. God.